Hello, this is Dr. Joe Trout from the physics program at Stockton University. This is Chapter 18, a celestial census. So if we look up into the sky, we see a variety of stars. And stars come in a variety of sizes, masses, temperatures, and luminosities. This image shows part of a cluster of stars in a small magnetic cloud. It's located about 200,000 light years. And a light year, don't forget, is the distance that light travels in a year. And it's about 65 light years across. Because the stars in the cluster are all about the same distance from us, then the difference in their apparent brightnesses correspond to differences in the luminosities. Differences in temperature account for the differences in color. And the various colors and luminosities of these stars provide clues about their life stories. So this shows a computer simulation, and this computer simulation shows the stars in our neighborhood as they would be seen from a distance of about 30 light years away. So the sun is at the centers, and all the brown dwarfs are circled, and those found earlier are circled in blue, and the ones that are found recently with the WISE infrared telescope in space are circled in red. So you can see we can start to, as we improve our observing techniques, we can see more and more of these low luminosity stars, right? The stars that aren't as very bright. So the common M stars, which are red and faint, are made to look brighter than they really would be so that you can see them in the simulation. So note that the luminous hot stars like our sun are very rare. So if we look at the closest stars, so the first image A was taken with a wide-angle telescope at the European Southern Observatory in Chile. And it shows the system of 3 stars that is in our nearest neighbor. In B, we see 2 bright stars that are really close to each other. This is Alpha Centauri A and B. And if you didn't have those 2 yellow dots to show you where the stars were, you would think they were just one star. So they're so close together that all it looks like is one giant star. In C, if you look, there's a arrow there, and it's there because you would barely notice it in the picture. And it's a much fainter star, which is of a spectral type M. So if we look at these binary stars, right, this shows the revolution of a binary star, and this figure shows 7 observations of a mutual revolution of 2 stars. One's a brown dwarf, and one is an ultra-cool L dwarf. Each of the red dots on the orbit, which is shown in the blue ellipse in the center, so if you look here, that's the actual orbit of the stars, corresponds to the position of the dwarfs relative to one another. So the reason that the pair looks so different in the different dates is that some of the images were taken with the Hubble Space Telescope and others were taken from the ground. And the arrows point to the actual observations, that corresponds to the positions of the red dots. From these observations, an international team of astronomers directly measured the mass of the ultra-cool brown dwarf for the very first time. So this was barely the size of the planet Jupiter, and the dwarf star weighs in at just 8.5% the mass of our Sun. So you might think if there was a binary star that it might act like our solar system, where we kind of consider the sun to be stationary and the planets revolving around it. So your first thought might be that if you have a high mass star and a low mass star, that they would actually, the low mass star would orbit around the high mass star. But this isn't what happens. What they do is both orbit around the center of mass. So what's the center of mass mean? Well, think of taking the high mass star and the low mass star and putting it on a seesaw. If both the stars were exactly the same mass, and they were on Earth, and they had exactly this, they would therefore have exactly the same weight. And in that case, the center of mass would be halfway between them. But since the high mass star is a higher mass, if we wanted to balance these so that the seesaw would remain horizontal, what we'd have to do is move this point called the fulcrum closer to the high mass star. So you can think of the center of mass as being the place where you would balance the mass of these two stars. So the high mass star would be closer to the center of mass, and the low mass star would be further away. And they both orbit around this center of mass. So you might think, well, when these two masses, these two stars are so close together that they look like one bright big star, how do we actually detect them? And one way we can detect them is by looking at the spectrum that we observe from the two stars. So if you remember, normally what we'd see is that we'd have an absorption line on the spectrum, and when both the stars are in line, if we're looking at it from the Earth, then what we see is that there's one absorption line. However, consider figure 1, and what's happening here is B is moving away and A is moving towards us, so we're observing it from, say, down at the bottom of the page and looking out in that direction. So in this case, star B is moving away from us and star A is moving towards us. Or star B is receding and star A is approaching us. And what happens is that if you remember, if we have stars that are moving towards us, then that spectral line will get blue shifted or shifted towards a shorter wavelength. And stars that are moving away from us get red shifted. So what we see is that when they were both in line with one another, we had one absorption line that was around green, and now we have A's absorption line is towards the blue end, and B absorption's line is towards the red end. So as time goes on, later we see that B is now approaching us and A is receding from us. So what happens is A's spectral line gets red shifted and B's spectral line gets blue shifted. So by looking at these spectrums, we can now see that there really are two stars, and we can also get some idea of their radial velocity. by looking at their Doppler shift. So if we look at the radial velocities in a spectroscopic binary system, then these curves plot the radial velocities of the two stars in the spectroscopic binary system. And these show how the stars alternatingly approach and recede from the Earth. Note that the positive velocities means that the star is moving away from us relative to the center of mass of the system, which in this case is 40 kilometers per second. And the negative velocity means that the star is moving towards us relative to the center of mass. The position on the curve corresponds to the illustration shown in figure 18.6, and they are marked in the diagrams 1.1 to 4. So for example, in 1, A is moving slowly towards us, and B is moving faster away from us. So what we see is blue, we see that its absorption line is red shifted, and A, its absorption line is blue shifted. When they're both moving at the same position or the same velocity, we have A plus B, and that's position 2, and what we see is that the lines overlap. And then at 3, what we see is that in this case, if we look for A, it's moving away from us and B is moving towards us. So A is red shifted and B is blue shifted. So if we can't tell from the actual photograph, so the visible light, and it looks like just one giant star, if we look at the spectroscopy and we look at it over time, we can actually figure out if there's actually two stars there and one of them is just too dim to see. So these show brown dwarfs in Orion, and these are images were taken with the Hubble telescope, and shows the region surrounding the Trapezium star cluster inside the star-forming region called the Orion Nebula. In picture A, there's no brown dwarfs are seen in the visible light image. So this was taken with just visible light. And it's because they both put out very little light in the visible, and because they are hidden within the cloud of dust in this region. If instead we just look at the infrared light, right, it can make its way through the dust. And the faintest objects in this image are the brown dwarfs with masses between 13 and 80 times the mass of Jupiter. So we look at the mass luminosity relationship, and if we look at the solar masses, so we start at 0 and we end up with one solar mass, which is about the mass of our sun. So our sun would end up here somewhere, and this is 20 times the mass of our sun. And what it shows is that for the most part, as the mass increases, the luminosity increases. So if we look off of this sequence, so most of the stars lie within this line. However, also shown are 3 points below the line, and these are white dwarf stars. So even though they have them, for instance here, this about has the mass of our sun, but the sun's luminosity is about 1. Well, it is 1. And the brown dwarf, its luminosity, don't forget this is a log scale, so it's about 1/100th the luminosity of the sun. By the way, if we do have light curves on an eclipsing binary, what we could also do is just look at the brightness as we observe it. So what we see is if we look at point 1, we'll be getting all of the brightness or all of the light from both the stars. And what we'll end up with is this maximum brightness here. If we look at 2, the smaller, dimmer star that we couldn't see goes behind the planet, and suddenly our intensity decreases. And then it comes out from behind the star, and as it comes out from behind the star, the light curve goes back up to its maximum brightness. And eventually the star is between the lower mass, lower luminosity or lower brightness star is in front of the higher brightness star, and what it'll do is block out some of that light from the brighter star. So our brightness will be dimmer, but not as dim as when the planet goes behind, when the lower mass star goes behind the larger mass star. If you notice, there's a slope between points 1 and 2. Okay? So this isn't a straight line, it's kind of curved and it has a slope. And if I look from 2 back to 3, there's another line and it has also a slope. So what we're seeing here is that as the star travels in front of as the low mass star travels in front of the high mass star, we can get an idea of what the diameter of that star is. So now, if we could measure the distance, right, this is just before it starts to go in front of the star, and then as it's starting to move into the star, the intensity gets less and less, and then when all of it's in front of the star, it reaches its minimum. So all we have to do is measure this distance here, and we'll know what the diameter of that low mass star is. So it's good to look at different characteristics and try to find a relationship between them. So just as an example, here's the height versus weight of a large selection of human beings. And what you see is that most of the points lie along this main sequence. All right? And don't forget, weight is increasing in this direction. So this is a small weight, and this is a large weight over here. And height is increasing up. So not surprisingly, the taller you are, the more you weigh. And the shorter you are, the less you weigh. So for most people, as they get taller, their weight increases. There are some exceptions. Here's somebody who's really tall and really skinny. Right? So they don't weigh much at all, but they're really tall. And here's somebody who's not so tall, but they're overweight. However, most people lie along this line here. We'll call the points that lie along this line, or we'll call this line, where most of the points lie about the main sequence. So Hertzsprung and Russell both came up, they discovered a relationship between the luminosity and the surface temperature of stars, and it's summarized in what we now call the HR diagram. So they came up with it independently and about the same time, so they're both given credit for it. So here we see the HR diagram for some selected sample of stars. As in our last diagram of height versus weight, what we see is that you can either plot it against spectral classes or temperature, but the temperature is increasing towards the origin, right? So this is 3,000, this is 25,000. Don't forget, the hotter the star is, right, the shorter its wavelength. So these cool stars are reddish and these hot stars are bluish. And this shows the spectral class. Don't forget, our sun is spectral class G, and it's about right there, right? And the luminosity is shown in relationship to our sun. So this is the same luminosity as our sun. So Alpha Centauri is awful close to the same luminosity as our sun. This is 100 times the luminosity, and 10,000 times the luminosity. And this is 1/100th the luminosity of our sun. So in such diagrams, the luminosity is plotted along the vertical axis, and along the horizontal axis we can either plot temperature or spectral type, also sometimes called the spectral class, and several of the brightest stars are identified by name, and most stars fall along this main sequence. So it's not a straight line, but it gives us an idea of what happens as the temperature increases. So this shows a schematic HR diagram for many stars, and once again it's plotted against spectral class or temperature, and 90% of all the stars on such a diagram fall along this narrow band that we call the main sequence. And a minority of stars are found in this upper right region, right? So they're cooler and brighter, right? So they're cooler and brighter than the stars, and therefore they have to be giants. And some of the stars fall in this little lower left portion of the diagram, so they're off the main sequence, and they're both hot and dim, and they must be white dwarfs. If we look at a supergiant star, right here we show it in relationship to the sun, and it's just amazing, right? So this is the orbit of the Earth, is that dotted blue line, and the sun's in the center, and then we see VX Canis Majoris, right, which is a supergiant star. Here we see two views of Sirius and its white dwarf companion, right? So these are binary stars, and the first shows visible light that was taken with the Hubble telescopes, and it shows the bright Sirius A, and below it and off to its left is the faint Sirius B. In image B, the image of the Sirius star system was taken with the Chandra X-ray telescope. Now the bright object is the white dwarf companion, Sirius B. And Sirius A is the faint object behind it. Right, or just above it. And what we're seeing is that Sirius probably is not actually an X-ray radiation, but probably ultraviolet light that is leaked into the detector. But note that the ultraviolet intensities of these two objects are completely reversed from the situation in the visible light spectrum, visible light photo. Because Sirius B is hotter and it emits more high frequency radiation. Okay, and that ends chapter 18, and thanks for your time.